Hey everyone, my name's Ray, for those who don't know me. I'm very excited to be talking with you today about covariant balance of potential unmeasured confounding using large-scale propensity score modeling. So this stems from work that I did with George Ripsack as part of my NLM fellowship at Columbia DBMI. And I really like to thank my co-authors and collaborators on this project, which are Martijn Schumi, Mark Suchard, Anna Stropolitz, Ling Zhang, Patrick Ryan, and George Ripsack. I recently moved over to Geisinger as an assistant professor of research. And just a quick plug for Geisinger, we do have an OMOP with over 2 million patients on the same EHR for almost 25 years, and look forward to collaborating with you guys on future studies. So in large-scale propensity score modeling, we often use tens of thousands of measured covariates in regularized regression to determine the likelihood of each cohort's likelihood of getting the treatment under investigation. But the question often comes up in reviews of observational research: what about unmeasured confounding? Certainly we might assume that we can't balance or really investigate what we cannot measure and don't have in our database. But there may be an underlying idea that many measured covariates could have potential relationships with some of these unmeasured confounders. So what we have in the data may somehow account for some of the things that we can't see. So just as a quick example, say we're doing a study on stroke. We all know that hypertension is a big risk factor for stroke and should be a big part of any study involving stroke. But let's say for some reason somebody accidentally wiped out the conditions table, or there's just somehow no diagnosis of hypertension in your database. So if that's gone, and yet with the rest of the data, say we still have things like measurements, drugs, and we have antihypertensive drugs, could we use the rest of the data to still be balanced on hypertension somehow? Effectively, the research question is, how well does large-scale propensity score modeling and adjustment using cohort method balance on sets of held out, which essentially are modeling unmeasured covariates, if we're balanced on the remaining measured covariates? So if we can balance on, say, 10,000 covariates, how vulnerable are we to residual unmeasured confounding? So for this study, we used two data sources just to try to ensure that this works on multiple databases. First is the Columbia University Irving Medical Center. It is an electronic health record database. And as you know, it's an academic medical center. Then the second was CCAE, which is part of IBM MarketScan, which is a claims database, private payer. The cohorts are from the previously published Legend hypertension study. So what we did was we compared new users of lisinopril with new users of amlodipine. And the reason I picked those two was essentially because those are two of the largest cohorts. So we wanted to see if they could work on some of the these two groups. That is the preference score distribution, which is essentially a transformation of the propensity score for those two cohorts. And you can see in terms of distribution, there's a good amount of overlap, which is why we felt this was a valid comparison in the original study. Less relevant for this, but essentially, we wanted to look at covariate balance within those two groups. What we did was use cohort method to extract patient features and covariates. Then we generate large-scale propensity score models with and without these held-out test sets. And we once again measure covariate balance again after we add back what we took out. So some of the things that we held out include conditions, procedures, drugs, all cardiovascular related concepts. And then we, just as kind of a sanity check, we took out everything except demographics. So what this means is that into the model, say if we're holding out conditions, we put everything else in except for conditions, generate the model, and then add back conditions and see if we're still balanced on everything. And here's what we found. Just as a quick overview of how these covariate balance plots actually look like and work. Here on the x-axis, you have the distribution, the standardized difference of the mean for all covariates before matching. And so this would either before propensity score stratification or propensity score matching. And you can see that some of these dots are way far out at 0.6 or 0.5. So you can see that they're not all necessarily well balanced. And then after matching, the vast majority, actually all of them, are under 0.1 for a standardized difference, which means after matching here on the y-axis, we actually do quite well after we've done this propensity score adjustment. So diving into the results for CMC. So this is how the plot looks with all covariates. We know we achieve good balance. This is what we did for the legend hypertension study using large-scale propensity score adjustment. All right, and here are our results. So at Columbia, using propensity score matching, this is our results for the various held out test sets. So first, this is with all the covariates in the model. You can see we balance quite well, as you saw in the previous plot. This does not work if you only put in demographics. You can see there is still 233 covariates that remain unbalanced. But in all the other test conditions of holding out conditions, drugs, procedures, it actually balances quite well, and maybe slight concern with 3 remaining unbalanced covariates for when we hold out cardiovascular related concepts. A very similar story is found under using propensity score stratification on Columbia. So except for there is slightly more unbalanced covariates when we hold out drugs. So it seems like drugs may be adding a little bit more to the picture, or a little bit more important. Visually, this is what it looks like. You can see when we hold out procedures, we still look very similar, that things remain well balanced here after matching. But then if you just use the demographics here as and balance only on those, it does not work when you add everything back in. Then for CCAE, once again, very similar results, does not work for demographics. Some concern here with drugs. Everything else remains actually well balanced despite holding them out. And using propensity score stratification, once again, very similar. Still drugs and demographics are the main ones that remain unbalanced. And then there's that one lonely covariate in conditions that remains unbalanced, so we hold that out. So our key finding here is that large-scale propensity score modeling, as implemented in cohort method, balances well across a variety of different held-out test sets, modeling unmeasured covariates. There are a few limitations to this. We did this across 2 large databases, EHR Columbia, CCAE for claims. The two cohorts that ran this on were based on one large network study, legend hypertension, for a common indication. So we don't know if we'll expect similar performance in smaller databases or cohorts, but we certainly hope so. And so future work, we try to extend this to those other different types of scenarios to see if it still works. So in conclusion, we feel that large-scale propensity score modeling may be effective in achieving covariate balance, even for those covariates which are not directly measured. This effectiveness of this balance may depend on whether some of these potential unmeasured confounders have some relationship with those covariates that are in the data. And this helps us to have a little bit more confidence in those estimation studies that we're running that have good data coverage for the topic of study. So if there's a lot of hypertension related concepts in your database, we feel better about some of the results and conclusions that we can reach with our studies on hypertension, for example. And with that, I thank you for your attention. I look forward to collaborating with you, and I'm happy to answer any questions. All right, thanks everyone.